Hi, I am Aditya Baswaraj Mali, studying in Sri Venkateswara College of Engineering, Bangalore. Today I am going to cover the topic sparse matrix multiplication and multiple queues. Optimizing sparse matrix multiplication using multiple queues. Introduction to the sparse matrix multiplication. Sparse matrix multiplication is a critical operation in various applications, particularly in scientific computing and machine learning. This presentation explores optimizing this process using multiple queues to enhance performance and efficiency in computation. Understanding sparse matrices. A sparse matrix is a matrix in which most of the elements are zero. This characteristics allows for specialized storage and processing techniques that can be significantly reduce computational costs and memory usage when performing operations like multiplication. Why to use sparse matrix instead of simple matrix? First reason is storage. There are lesser non-zeros elements than zeros, and thus the lesser memory can be used to store only those elements. And the next reason is computing time. Computing time can be saved by logically designing a data structure traversing only non-zero elements. Example is 00304, 00570, 00000, Representing a sparse matrix by a 2D array leads to the wastage of lot of memory as zeros in the matrix are of no use in the most of the cases. So instead of storing zeros with the non-zero elements, we can only store non-zero elements. This means storing non-zero elements with the triples, that is rows, columns, values. Sparse matrix representation can be done in many ways. Following are the two common representation. First one is array representation and the second one is linked list representation. Method 1. Using arrays. 2D array is used to represent a sparse matrix in which there are three rows named as row, index of the row when non-zero element is located, column, index of column when non-zero element is located. Next one is value, value of a non-zero element located at an index. Time complexity in array representation, O into nm, where n is the number of row in the sparse matrix and m is the number of columns in the sparse matrix. Auxiliary space, where n is the number of rows in the sparse matrix and m is the number of columns in the sparse matrix. Next method is using linked list. In the linked list, each of the node has a four fields. These four fields are defined as row, column, value, next node. The first one is row, index of the row when non-zero elements is located. Column, index of the column where non-zero elements is located. Value, value of the non-zero elements located at index, that is row, column. Next node, address of the next node. Real-world applications. Sparse matrix multiplication is widely used in the fields such as machine learning, data mining, and scientific simulations. Our optimization techniques can vastly improve the performance of these applications, making them more efficient and scalable. Performance matrices. When evaluating the performance of our implementation, we focus on matrices such as execution time, memory usage, and throughput. These matrices help us to assess the effectiveness of using multiple queues in our approach. Case study. Several case studies demonstrate the effectiveness of optimizing sparse matrix multiplication with multiple queues. These studies highlight significant improvement in processing speed and resource management in various applications. Challenges in sparse matrix multiplication. The main challenge in sparse matrix multiplication include handling irregular data patterns and managing memory efficiently. These issues can lead to increased computational time and resource consumption if not addressed properly. Introduction to the multiple queues. Multiple queues are the data structure that allows for a parallel processing tasks. By the leveraging multiple queues, we can improve the throughput of matrix multiplication operations by distributing workload effectively or efficiently across available resources. Benefits of using multiple queues. Using multiple queues can lead to better resource utilization and reduces waiting times and improve overall performance in the sparse matrix multiplication. It allows for concurrent processing, which is essential in high performance computing environment. Implementing multiple queues. To implement multiple queues, we can divide the sparse matrix into smaller blocks and assign each block to the separate queues. This allows for independent processing of each block, thereby enhancing the efficiency of the multiplication process. Algorithm design. The algorithm for optimizing sparse matrix multiplication using multiple queues involves defining the queue structure, task assignment, and synchronization mechanism. This ensures that the tasks are processed efficiently without conflicts or bottlenecks. Conclusion. In conclusion, optimizing sparse matrix multiplication using multiple queues offers a significant benefits in performance and efficiency. By addressing the challenges and leveraging modern computational techniques, we can enhance the capabilities of various applications. Thank you.